Okay, so this will wrap up the semester. This is a short video introducing the final exam and kind of summarizing what we've done in this course. So we've looked at networks and classifiers. We looked at big data, seeing that it's complex and high dimensional. And we've looked at a lot of different methods. We haven't looked at ensembles yet, but we're going to look at those also. So what we have looked at are some classifiers. Some have been intuitive but limited. So graph clustering, the sub-economy problem, the small town zoo, the k-nearest neighbors, decision trees. These are easy to interpret and they're easy to use, but they're also unstable, difficult to reproduce results, sensitive to small variations in the data. Then we had some classifiers that were mathematically accessible, entropy-based methods, but they required an assumption of linear separation, and if the assumption doesn't hold, then the results are not valid. We also have some powerful but very deep and abstract ideas that we just barely began to scratch the surface with. Support vector machines, because we didn't do more with support vector machines, because to actually work with them requires a field called quadratic programming, which is linear programming with a quadratic objective. It also requires us to know something about non-Euclidean norms and inner product spaces. By the way, Operations Research 2 covers quadratic programming. Computationally, all we really needed was some familiarity with object-oriented programming. Ensemble methods are also deep and abstract and very powerful. The one we'll look at the most is a random forest. So for some familiarity with ensemble methods, we need graph theory, bootstrapping, more precisely sampling with replacement. To really have a good idea of what's going on, however, we need some pretty advanced ideas, and we need to be very deeply immersed in statistical methods, because ensemble methods can produce nonsense, and we need to be able to statistically infer whether or not a result we got is nonsense. Computational, really using random forests is something very straightforward for us, even where we are right now. Neural networks are powerful. They're also deep and abstract. A minimal exposure means that we have to have some ability to recognize and utilize universality, overfitting, and the vanishing gradient problem. Everything above a minimal use of neural networks requires extensive background, both mathematically and computationally. But that doesn't mean that we didn't do something valuable in getting a minimal understanding. Even a minimal understanding of a very powerful idea can be a very powerful thing. Now, my original goal was we would go up through logistic regression, and we would get sort of a feel for each of the things beyond logistic regression. But I realized there's a disadvantage. People get confused between support vector machines and neural networks. They both generalize logistic regression, and some instances of support vector machines are actually artificial neural networks and vice versa. Also, support vector machines are rather easy in some sense in comparison to artificial neural networks, and so when people see both, they tend to prefer the support vector machines over the neural networks, which is not a good thing. So I said, let's have a new goal. We'll just at the very end get the basic concepts for support vector machines and ensemble methods, and instead we'll get a pretty good minimal understanding of artificial neural networks. So this is what we're doing now. And our focus still will be on neural networks, even though we're going to just introduce the bare concepts of the other two. And this is your final exam in a nutshell. Goal number 1, you'll get a grade. But much more important probably is goal number 2. And the reason I created this course is not to be a traditional course, but the fact that the things that we're doing in this course, as you'll see on the final exam, these are things that people are being hired to do. As a matter of fact, there's a huge shortage of people that can do these things. So support vector machines, let's just get a very brief introduction to this idea. It's based on a very simple idea that if data is not linearly separable in dimension m, it may still be linearly separable if you embedded it in some higher dimensional space, especially if n is very large. And notice what this does is it puts the curse of dimensionality to work. Remember, the curse of dimensionality says that in higher dimensions, data points tend to be rather far apart. But if data points tend to be rather far apart, it tends to be a lot easier to stick a hyperplane to separate points. So the problem becomes, well, how do we embed into higher dimensions? So we've actually already seen support vector machines intuitively several times in this course. We talked about this linear separation. And mathematically, we could derive the support vector machine concept from the intuition we have so far. So we have a data set that can be separated linearly by a plane or a hyperplane or a line in 2 dimensions. And notice that in order to do this separation, all we really need to do is find these 2 magenta lines, one that has all of the class 1s above it and one with all the class 0s below it, and you find the 2 optimal such lines, and then you can define the support vector machine classifier to be the one that's in between, the average of those 2 pink lines. Now, so to reiterate, we don't really need the blue line at all. So let's just kind of get rid of it. And we don't really need all the data. We just need the ones that determine these 2 separating lines, these 2 magenta lines. And this is what's known as the margin. And so all we need are those vectors that determine what the margin is, and those vectors are called support vectors. And so we have a task, and the task is to find some vector w in Rn such that the inner product of w and x is 1 if x is in class 1, and -1 if x is in class 0. And that corresponds to w then would give us these 2 parallel pink hyperplane separators. So what does it mean to embed into higher dimensions? So it means a linear transformation. And what does this linear transformation need to do? It needs to have a vector x with m coefficients mapped to a vector tx with n more than m coefficients. So as a matrix, T would have more rows than columns. And we want the norms to be the same, and we want T to be 1 to 1. So we want it to be a true embedding. But notice that in the task that we saw on the previous slide, all we use is the inner product. So the method only involves inner products. We don't actually ever use the vectors themselves in n-dimensional space. Therefore, we can embed into higher dimensions by choosing a kernel, a function of 2 variables, which satisfies that it's equal to the inner product of the embedded x and y's. But because it has to be an inner product, we can't just choose any kernel. So it has to have certain properties. And in particular, it's going to have to imply an inner product space on some abstract, very high dimensional vector space. It won't typically be the standard inner product. Instead, it will satisfy some abstract concept of what it means to be an inner product. And so that gives us a method, given a large data set. Choose an appropriate kernel function. Find the vector that implements the task using only a subset of the original data. Ultimately, the support vectors will be used or required. And we'll get this using calculus and linear algebra using a process called quadratic optimization over the kernel map data. The observations will then imply the support vectors. And the support vectors turn out to be extremely useful in dimensionality reduction, feature selection, all sorts of things. Ensemble methods have a very simple motivation. Entropy is an average. And so maximum entropy models from averages over many independent trials or observations are what we would ultimately like all of our models to be. And so we use sampling with replacement, so the next sample is independent of the previous. So this kind of models this averaging over many independent trials. An example that we'll look at is called random forests. You randomly choose a small collection of features and you create a decision tree, just like we did previously. Only you create a whole bunch of these decision trees and you average over the results. Here's the actual method. So for some large data set and some large number of trials and some fixed number of trees, you randomly select features and calculate, create a decision tree. And you create some fixed number of those decision trees, and then each tree gets to vote on what the classification of an input pattern is, and the classification with the most votes wins, and then you average over all those different trials. And that gives you a classifier that's essentially decision tree, but decision trees that are randomly generated and averaged over. Now, intuitively, what we're looking at is the fact that decision trees are unstable, they're ultra-sensitive, they're myopic linear classifiers, and they tend to overfit. So we generate huge numbers of such classifiers and throw out the ones that have those problems and average over the ones that don't have the problems. So this is essentially what ensemble methods do. Throw out the bad ones, keep the good ones, and average over the good ones to get a prediction. There's a problem, and that is these won't throw out everything when everything deserves to be thrown out. So it's very typical to end up with trials in which you should have thrown out everything and didn't. Now, neural networks, finally, are universal. So in some abstract sense, they're the most powerful method. They can do anything. They're classifiers, and they do a better job than logistic. They can be used for curve fitting, as we've seen a little bit. You can use them for matching and content-associative memory. You can use them for artificial intelligence. You can build robots and put artificial brains in robots using neural networks. But universal also means that these methods can have a mind of their own. You get lots of issues when you use neural networks. Overfitting, vanishing gradients, spurious states, just a huge number of things. And it may take hours, days, months, well, we wouldn't use years, but it can take a long time to train a neural network. And here's an example of the vanishing gradient problem. And you'll see this on the final exam where you'll hit shift enter, and it'll stop immediately, or it may do a 3 or 4 and then stop, and the error will be really high. So what you're hoping for is to get to the point where you get the little star and you get the kernel busy up there in the upper right, and then you start seeing over different epochs, you start seeing errors, and the errors are going down. And ideally those errors would go down to 0, but they should keep going down. As long as they're going down, you're training and you haven't run into the vanishing gradient problem.